Hey, this is Horner, and these are the problems, part of the problems that could be on the test, or I'm sorry, on the quiz on Wednesday. Make sure that you also know the problems from sections 1 and 2. So these will be sections 3 and 4 problems. And they do not come from your book, so they're actually on the sheet that you should have. If not, I'll put a copy on the ACE site. So here we go. We have a 0.055 Tesla magnetic field passing through a circular ring. It has a radius of 3.1 centimeters, which we know needs to be converted to meters. So that'd be 0.031 meters. Has a 16-degree angle with the normal. They want us to find the magnitude of the magnetic flux through the ring. So this one's pretty easy to do. We know that the magnetic flux is equal to B times A times the cosine of the angle. We do have an angle here, so we definitely need that. Magnetic field is 0.055. We're going to multiply that times pi r squared, so pi times 0.031 squared, so that would be our area. And then we need to take that times the cosine of 16 degrees. Make sure you're in degrees and not in radians, and you should end up with about 1.6 times 10 to the negative 4th Webers. And that is your answer to number 1. Let's go ahead and take a look at number 3. That's the next one. We have a magnetic field here at an angle of 47 degrees to the normal. We have an area of 5.1 by 6.8 centimeters. We need to convert these, so this would be 0.051 and 0.068 meters, respectively. The magnetic flux is 4.8 times 10 to the negative 5th Teslas times a meter squared, so definitely want to make sure everything's in meters. What is the strength of the magnetic field? So for this one, same thing. This time we're going to solve for B, so B is equal to the magnetic flux, all divided by A times the cosine of the angle. So here we have 4.8 times 10 to the negative 5th Teslas times a meter squared, all over 0.051 meters. That would be your length and your width, respectively 0.068. So length and your width, and then times the cosine of 47 degrees. So these two things, remember, will give you area, and you end up with a magnetic field of 0.02 Tesla. And that is the end of number 3. Let's go on to the next one, number 5. This one says a magnetic field produced by an MRI solenoid is 2.5 meters long and 1.2 meters in diameter, and has a magnetic field of 1.7 Tesla. They want to find the magnetic flux through the core of this solenoid. So same equation again that we've been using. The flux is equal to B times A times the cosine of the angle. This one we're going to have to make sure that when we have this diameter, we divide it by 2 to get our radius. And so let's go ahead and do this one. Magnetic field strength is 1.7 Tesla. Our area here is going to be pi times the radius squared. So we'll do 1.2 over 2. So that's diameter divided by 2 is radius, and we can square it. And then this is times the cosine of 0 degrees. Since it is the magnitude of the flux through the core of the solenoid, so 0 degrees is our angle for BA here, and so when you multiply those through, you should end up with 1.9 Webers. And that one is number 5. For number 6, at a certain location, Earth's magnetic field has a magnitude of 5.9 times 10 to the negative 5th, and it points in a direction 72 degrees below the horizontal. Find the magnitude of the magnetic flux through the top of a desk at this location that measures 130 by 82. So essentially what you have in this one is you've got a desk that kind of looks like this. This is from the side, and the magnetic field is coming down through the desk. The desk has this 130 by 82 centimeter area here, and when we do this one, it says that the direction here is 72 degrees below the horizontal. So here's the horizontal. This would be our 72 degrees, and we actually need the angle to the vertical. So we want this other angle, and this is the angle that we want. So we're just going to take 90 minus 72. That's going to give us an angle here of 18 degrees. So we always want the one with the vertical for when we do this one. Alrighty, so here's the flux. Flux is equal to BA times the cosine of that angle with the table there. So here we've got 5.9 times 10 to the negative fifth Tesla times our area, which is going to be 1.3 meters times 0.82 meters. So these two together, length times width, will give us our area, and then that's times the cosine of 18 degrees, because that's the angle that we need to have with the normal here. And so when we're done, we should get 6 times 10 to the negative fifth Webers. For the next question, that is number 7. Here it says I have a solenoid with 385 turns, should be per meter, and a diameter of 17 centimeters, has magnetic flux through its core magnitude, and then they give us the magnitude. Remember, your diameter here should be in meters, so that's 0.17 meters. Okay, and so what we've got to do here is we do have B, which is equal to the flux divided by the area. Our flux here is 1.28 times 10 to the negative fourth, and then our area is going to be pi times, we need to do r squared, so this is going to be point, so half of 17 should be 0.085, and then we've got to square that, so we should end up with 5.64 times 10 to the negative third Teslas. That would be the magnetic field. So now they want us to find the current. So we can do that using B is equal to mu O times N times I. I here then is equal to B over mu O times N. So we have 5.64 times 10 to the negative third. Then we need to divide that by mu O, which is 4 pi times 10 to the negative seventh, and then make that times the number of turns per meter, which is 385. And so our current here is 11.7 amps. It says, how would your answer to part A change if the diameter of the solenoid were doubled? The current would be cut to 1/4. So if the diameter were doubled, then we half that diameter, but then you have to square that. So that's why we end up with 1/4 as we go through. Okay, so let's go ahead and take a look at the next one, which is number 9. And for number 9, I've got a 0.45 Tesla magnetic field. It is perpendicular to a circular loop of wire with 53 turns and a radius of 15 centimeters. If the magnetic field is reduced to 0 in 0.12 seconds, what is the magnitude of the induced EMF? So remember, this is absolute value of the EMF is equal to the number of turns times the change in the flux divided by the change in time. We also said earlier when we were going through notes that that would be BA, which is the flux minus 0 since it goes to 0. Okay, and then we need to divide that by the change in time, and so the number of turns is 53. We're going to take that times 0.45 Teslas times pi. And then we've got to have the radius, which is 0.15. Be careful, make sure you convert it to meters. 0.15 meters squared. This is pi. I know that looks funny. And then we're going to divide that by our 0.12 seconds. So when we're done, you should get about 14 volts. That is number 9. Let's go ahead and take a look at the next one. Number 10, this one's got a graph with it. It says the figure shows the magnetic flux through the coil as a function of time. At what time shown in this plot do the magnetic flux have the greatest magnitude. So the greatest magnitude for the flux here is going to be at 0 seconds, so that's where it's way up here at 4. It also is at 0.2 seconds. So here, greatest magnitude, we don't worry about direction, so that's also at 0.2 seconds. We can then also have it at 0.4 seconds and then finally at 0.6 seconds. And then the magnitude of, it says the induced EMF have the greatest magnitude. And this is where we're going to have the flux here is changing by the most amount. So that's where you have your slope is the steepest. So here this is going to be 0.1 seconds, 0.3 seconds, and 0.5 seconds. When the flux is 0. So here our flux is 0 right here, and right here, and that's when the induced EMF should have the greatest magnitude. The magnitude of the induced EMF is 0 actually when we have maximum amplitude. So here this would be 0, here your EMF would be 0, here your EMF would be equal to 0, and here your EMF would be equal to 0, and that's where the flux has got the greatest magnitude. EMF would have the greatest magnitude at the points where our flux is actually 0. Alrighty, so let's go ahead and take a look at the next one. This is number 11. The figure shows the magnetic flux through a single loop coil. So our N value here is going to be equal to 1. As a function of time, says what is the induced EMF in the coil at, and they have t is equal to 0.05 seconds, so that's going to be about right here. T is equal to 0.15 seconds, which is about right here, and then t is equal to 0.5 seconds, which is the what we see right here. So if you remember in class, we said that the EMF is equal to negative n times, now my pen's going to screw up here, is equal to negative n times the change in, I'm going to have to just move this over, change in flux. Oh boy, I just have to move this whole thing. All right, here we go. So N, E is equal to negative n times the change in the flux all over the change in the time. Here we've got one coil, so we just do 1 there. This is going to be negative, and we say it's 10 Webers minus 0 Webers, so it's the final minus the original. So at this point, we just look for the slope of the line, and then we divide that 0.1 seconds, and we end up with negative 0.1 kilovolts. For letter B, we see that there is no change in flux at all. So here our induced EMF has got to be 0. And then finally for the last one, this is equal to, and notice we have negative 5 Webers, so that's final, minus the original, which is 10 Webers. And we're going to divide that by 0.6 minus 0.2. And so here we get 0.04 kilovolts, and that one's positive. So whenever you have a positive change in flux, you're going to get a negative EMF, and whenever you have a negative change in flux, you're going to get a positive EMF, and that's what you'll see as it goes through. That is number 11. Let's go ahead and take a look at number 14. It says the magnetic field flux through a single loop coil is given by the figure in problem 11. So that's that same picture that we just saw. They would say, is the magnetic flux at T is equal to 0.25 greater than, less than, or the same as the flux at T is equal to 0.55. So here is 0.55 about right there. And then T is equal to 0.25 is right here. So for this one, the flux here is about 8 at 0.25, and at 0.55 is about -3. So they wanted to know where is it greater, and so here we do say that it is greater than at that point. Then the next thing they want is the induced EMF at 0.25 versus 0.55. So the two EMF values are the same because they lie along the same line, which represents the change in flux. So one is here, 1 is here, and the change in flux is what determines the EMF. So the EMF here is constant. Okay, the induced current is constant from this point down to this point because that's where I have my change in my flux. For the next part of the problem, which is letter C, it says calculate the induced EMF at times 0.25 and 0.55. So to do that, we really just need the slope of that line. So here we're just going to say the EMF is going to be equal to the change in the, oh, you know what, we need to do N also here. So let's go ahead and just change this. Let's just look at the flux, change in flux over the change in time. Let's do that first. So this is equal to -5 Webers. That's our final minus original, which is positive 10, but we're subtracting it, over 0.6 minus 0.2. And so here we get -37.5 Webers per second. E then is equal to -N times that change in flux over the change in time. I guess we could have put that in here also. So that's -1 times -37.5. And we end up with our answer that we got earlier, which is 0.04 kilovolts. Now you kind of see where the negatives go and why that becomes a positive value. The next problem that we have is number 15. It says consider the single loop coil whose magnetic flux is given as the figure to the right. So you can see it's very sinusoidal here. Is the magnitude of the induced EMF in the coil greater at the first time they have there is 0.4 seconds, or is it greater at or near 0.5 seconds? So for this one, it's greater near that 0.5 seconds. Because if we look at the 0.5 seconds, the EMF is changing more rapidly there. Here, the EMF is really not changing at all. So, sorry, the flux is not changing at all. So the change in flux right here is essentially equal to 0, and here I have a large change in flux. And so if I have a large change in flux, I should have a bigger EMF. For the next part, it says what times in this plot do you expect the induced EMF in the coil to have a maximum magnitude? It should be at 0.1, at 0.3, should be at 0.5, and then you could just go on from there. And then they want us to estimate the induced EMF at the coil at times near 0.3, 0.4, and 0.5. So at 0.3 seconds, we're right here. You'll see there's a positive slope, which means I get a negative EMF. So that one's going to be, so this is at 0.3 seconds. So our EMF here is equal to -N times the change in the flux over the change in time. So that's approximately equal to -1 times, so we've got 2 Webers minus -2 Webers, and we're going to divide that by 0.333 minus 0.267. So we're kind of picking our numbers here pretty precisely off that graph, which is a little strange. And so this one is equal to -0.06 kilovolts. For the 0.4 seconds, this is going to be equal to 0, and we said it earlier because there's no change in flux at that point. And then finally for the last one, which is 0.5 seconds, it's going to be large because it's going to be positive. So it's the same value that we have here, but instead it's going to be 0.06 kilovolts. Math would be the same, except for we start with -2 here. And then our times are a little bit different too. So I'll give you that math. This is going to be approximately equal to, so EMF, same equation, is approximately equal to negative, the value -2 Webers minus 2 Webers, all over 0.533 minus 0.467. And that will give us that positive 0.06 kilovolts. And that one is number 15. For the next problem that we have, we're going to look at it. It's number 31. So it says if we have a long straight current carrying wire passes through the center of a circular coil. The wire is perpendicular to the plane of the coil. If they say if the current in the wire is constant, is the induced EMF in the coil 0 or non-zero here? And so it would be 0. And it's 0 because if we think about that coil, so here's our coil and there's our wire, we've got a magnetic field that it's coming out of the page on the top and it's going into the page on the bottom. And if that's true, and the coil is the way that we kind of show it here, there are really no field lines going through it. So the magnetic field is parallel to that plate. If the current in the wire increases, is the induced EMF in the coil 0 or non-zero? Well, it's still going to be 0, and it's because even though it's increasing, even though the current in the wire is increasing, the field's getting stronger, it's still not going through that little loop. And then it says, does your answer to part B change if the wire no longer passes through the center of the coil, but is still perpendicular to the plane? And your answer does not change. No, it does not change. And it's, so the wire no longer passes through the center of the coil, but it's still perpendicular to the plane. The magnetic field is still parallel to the loop. And if it's still parallel to the loop, it won't matter. So that's kind of the way that one works. Let's look at the next one, number 35. I have a conducting rod. It slides on two wires in a region of a magnetic field. The two wires are not connected. Is the force required to keep the rod moving? Is a force required to keep the rod moving with a constant speed? So for this one, the solution is no. And the reason here is the fact that the two wires are not connected means that there's no current. And so since there's no current flowing through the rod, the magnetic field exerts a 0 force on the rod. So no current, so then we would have no force due to the B field here. If that system is frictionless, no force is required to keep the rod moving, essentially. The next one that we have here is number 37. I have a Boeing KC-135. A airplane has a wingspan of 39.9 meters, flies at a constant altitude in a northerly direction with a speed of 850 kilometers per hour. It says that the vertical component of the Earth's magnetic field is 5 times 10 to the negative fifth, and the horizontal component is 1.4 times 10 to the negative sixth. They want to know what is the induced EMF between the wingtips. So I'm going to draw a stick airplane here. So here's our two wings, and then we've got our tail back here in the back. And then we've got this magnetic field which is moving up, and it's moving down past the airplane, kind of like this. So this is our crude picture that we're going to use. So we want to find out what is the induced EMF. So here the induced EMF should be equal to the velocity of the airplane times b times the length. Our velocity here is 850 kilometers per hour. We're going to need to convert that to meters per second. And so what we'll do here is we'll say this is 1 hour over 3,600 seconds. The magnetic field here, the vertical component, and that's the one that we want to worry about, is 5 times 10 to the negative sixth. 5 times 10 to the negative, 5 times 10 negative fifth Teslas. And then we also want 39.9 meters. That's the wingspan, so that's the length of the airplane from left to right. So that's kind of like that rod. So this one we then will go through and just solve, and you should get about 47 millivolts. And so because that plane is flying horizontally northward, the horizontal component of the Earth's magnetic field doesn't even factor into it. We're just worried about the vertical one, the one that's moving up and down. You know what? This is actually 5 times 10 to the negative sixth here. So that magnetic field should be 5 times 10 negative 6. That is a typo. So this was also 5 times 10 negative 6, and that's what gives you your 47. And that is the issue with that problem. Let's go ahead and go on to the next one. This is number 38 here. I've got a zero resistance rod. It is sliding to the right on a zero resistance rail, and the distance between the two rails is L, so that's the length of our rod. The rods are connected to a 12.5 ohm resistor like this, and the entire system is in a uniform magnetic field with a magnitude of 0.750 Tesla. They want us to find the speed at which the bar must be moved to produce a current of 0.155 amps. So let's go ahead and find that current. So to do that, we know that we have EMF is equal to I times R. Our current here that we want is 0.155, and we have 12.5 ohms for our resistance, so we end up with an EMF of 1.94 volts. So now we know what the voltage should be. We can use our equation. E is equal to V times B times L, and we can solve for V, which is the velocity, and that's equal to our E over our B times L. Our E here is 1.94 volts. We have a 0.75 Tesla magnetic field, and then the length of the rod is 0.45 meters. So we end up with 5.75 meters per second. Would our answer to part A change if the bar was moving to the left instead of the right? No. The answer would not change because the equation for V is basically just independent of the motion of the bar itself. And that is number 38. Let's go ahead and take a look at the very last one, which is number 39. So we're referring to this same picture that we had above. It says find the force that must be exerted on the rod to maintain a constant current of 0.155 amps in the resistor. So to do that, we just need the equation for magnetic force, which is ILB. Our current here is 0.155 is what they want. Our length is 0.45, and then the B value that we have is 0.75. So if we go through and solve that, we should end up with 52.3 millinewtons. The next one, they want the rate of energy dissipation, so that's just the power. So power here is I squared times R, since we have the current and the resistance, 0.155 squared times 12.5 ohms, and that's equal to 0.3 watts. And then finally for the last one, they want to know what's the mechanical power here, and mechanical power is just force times velocity, and so this is equal to 52.3 millinewtons. That was our force we found earlier. And then our velocity is 5.75 meters per second, so we end up with 0.3 watts. And that is the end of the problem set.